Hi, everybody. It's Professor Mitchell. We are finishing up Chapter 2 today on logic and sets. Today, we're going to talk about other set operations and their properties. So the objectives in this section are to study relations between set operations and logic connectives, and also look at Venn diagrams to sort and reason with data. So first, we'll talk about the intersection between two sets. Consider the following sets. C is the set of all X such that X is a college graduate. And S is the set of all X such that X earns at least $40,000. Suppose we wanted to mail a questionnaire to all individuals in a certain city, college graduates, and who earn at least $40,000. In other words, college graduates who earn $40,000. Then the individuals to receive the questionnaire include those common to both set C and set S. In other words, the people who belong to both sets. And that's called the intersection of those sets. So the intersection of sets C and S is the shaded region here. By the way, this is called a Venn diagram. And here is the definition. The intersection of two sets A and B, which is written like this with this kind of upside down U looking thing, is the set of all elements common to both A and B. In other words, A intersect B is the set of all X such that X is an element of A and X is also an element of B. Notice the key word for intersection is and. That implies both conditions must be met. So in this example, we'll find the intersections of a few sets, starting with A, which is the numbers 1, 2, 3, and 4, and B, which is the numbers 3, 4, 5, and 6. What do those two sets have in common? They have the numbers 3 and 4 in common, so that would be A intersect B. The next example, A is the set 0, 2, 4, 6, et cetera, et cetera, et cetera. In other words, even whole numbers. And B is the set 1, 3, 5, 7, et cetera, et cetera, et cetera. In other words, odd whole numbers. So what do those two sets have in common? They don't have anything in common. So the intersection of those sets is the empty set. And whenever that happens, we say that the sets A and B are disjoint. Disjoint sets have no elements in common. And then finally, we have A, which is 2, 4, 6, 8, et cetera, the set of even natural numbers. And then B, the set 1, 2, 3, 4, et cetera, which is all natural numbers. What do those two sets have in common? They have the even natural numbers in common. So notice in this case, A is a subset of B. And whenever that happens, then the intersection is just the smaller set. In other words, set A is contained entirely within set B. All right, if C represents the individuals with a college degree and S represents the individuals earning at least $40,000, we can use a Venn diagram to display information. For example, if we knew that 4,800 individuals have college degrees, 5,400 earn at least $40,000, and 1,200 have a college degree and make at least $40,000, then that means that there are 3,600 people who have college degrees but earn less than $40,000. So let me pause for a second here and point out, and I'll say this again later, don't read into a problem like this. When it says 4,800 individuals have college degrees, it's not saying anything about how much money they earn. So that includes people who are making more than 40,000 and people who are making less. Okay, so that's why we subtract the 1,200 because we know that those 1,200 are included within the 4,800. And then similarly, you can say that 5,400 minus 1,200, which is 4,200, earn at least $40,000 but do not have a college degree. And then you could summarize that information in the Venn diagram like this. And this is also a good place to check your work. Notice the 1,200 right in the middle, that's the intersection. And then 3,600 plus 1,200 is 4,800. We know that there are 4,800 elements in set C. 1,200 plus 4,200 is 5,400. We know there are that many people in set S. And that brings us to the union of two sets. So consider the same sets. And suppose now we wanted to mail a questionnaire to all individuals in a certain city who are college graduates or who earn at least $40,000 or both. Then the individuals to receive the questionnaire include those who are members of set C or set S. All right, and that's called the union of these two sets. So here's the Venn diagram showing union. Notice the whole entire region is shaded except for the part out here, okay? The part that's inside the rectangle but outside both circles, those would be people that don't have a college degree and also don't earn at least 40,000. So the definition of the union of two sets, union uses something that looks like a letter U. That is the set of all elements in set A or set B. And I think I mentioned this to you before in the logic section, I believe it was. Or in math almost always means and or, one or the other or both. Okay, so A union B is the set of all X such that X is an element of A or X is an element of B. And again, or means one or the other or both. All right, so using, I believe, the same sets that we were using before, now we'll find the union of A and B. So A is 1, 2, 3, 4, B is 3, 4, 5, 6. Which elements belong to A or B, or both? That would be the numbers 1 through 6, right? And remember, we don't list the elements of a set more than once. So even though the numbers 3 and 4 appear in both sets, you only list them once when you write the union. All right, if A is the set 0, 2, 4, 6, etc., and B is the set 1, 3, 5, 7, etc., the union of those two sets, the numbers that belong to either set or both, would be all whole numbers, right? Remember, this was even whole numbers, this was odd whole numbers, so the union would be all whole numbers. And then, if we have A as the set 2, 4, 6, 8, etc., B is the set 1, 2, 3, 4, etc., which elements belong to A or B? Well, it would be exactly all those elements that belong to B. Okay, because again, A is contained entirely within B. Whenever that happens, the union is just B. All right, another operation that you see sometimes with sets is called the set difference. So using the same two sets, if we wanted to talk about individuals earning at least $40,000, but who are not college graduates, that's called the complement of C relative to S, or the set difference of S and C. The complement of A relative to B, which is written like this, is the set of all elements in B that are not in A. So using set builder notation, that is the set of all X such that X is an element of B and not an element of A. And here they say, be careful not to read that as B minus A. I think I've been guilty of that actually. But I'm going to try to be careful from now on, because minus is an operation on numbers and set difference is an operation on sets. I personally think it's clear from the context you know, either you're talking about numbers or you're talking about sets. I don't think people would get them mixed up, but that's okay. So remember, let me just flash back here for a second. The definition of this set, it's the set of all x such that x is an element of B and not an element of A. So another way to write this set is to say it's the intersection, remember and, of the sets B and A complement, like you see here. And then the Venn diagram for that set looks like this. It's the set of all elements that are in B and are not in A. So for example, if A is the set containing the letters D, E, and F, B is the set containing A, B, C, D, E, F, and C is the set containing A, B, C, we will find the complement of B relative to A, the complement of A relative to B, the complement of C relative to B, and the complement of B relative to C. Okay, so I think the easiest thing to do is just remember that this set, it's everything that is in A but is not in B. Okay, so it's kind of a tricky example to start with. So you start off by looking at everything that is in A, but then you have to throw out the things that are also in B. And in this case, that's everything, isn't it? We have to throw out D because it's also in B. We have to throw out E, and we have to throw out F. So actually the complement of B relative to A would be the empty set. Okay, there are no elements that belong to A and not B. All right, but the complement of A relative to B is another story. So let's look at B, and then we'll throw out things that also belong to A. So we're throwing out D, E, and F, but we're left with A, B, and C. So the complement of A relative to B would be A, B, C. When we do the complement of C relative to B, let's see, we're looking at what's in C and throwing out stuff that's also in, no wait, I got that. We're looking at B and throwing out the stuff that belongs to C. So we have to throw out A, B, and C, and we're gonna keep D, E, and F. And then the other way, this last one is gonna be kind of similar to the first one, isn't it? All right, if I start in set A and throw out a set C and throw out everything that belongs to B, I'm throwing away everything. So the complement of B relative to C would be the empty set. Whew. All right, a few properties of set operations. First of all, intersection and union are commutative. It does not matter the order you write the sets. And I think that makes a lot of sense, doesn't it? If you're talking about all elements that belong to both A and B, that's exactly the same thing as saying all elements that belong to B and A, right? And the same thing for union. Everything that belongs to A or B is the same as everything that belongs to B or A. All right, intersection and union are also associative, which means that if you have to find the intersection or the union of three sets, it doesn't matter which two sets you find the union or intersection of first. Okay. All right, here's kind of a weird one, and I thought you might appreciate an example of this to help it make a little more sense. So this is saying that the intersection of the sets A and B union C is the same as the union of the sets A intersect B and A intersect C. So I sat and thought for a while, and I wish I could have come up with a better example, but here's what I came up with. So let's say that you were looking at some upper level history class, and it said, in order to take this course, you must be a senior and either a history major or a history minor. So imagine set A is the set of all seniors, set B is the set of all history majors, and set C is the set of history minors. I think you can convince yourself that this means the same thing as this. In order to take this course, you must be a senior history major or a senior history minor, right? All right. So let's look at this example. Use set notation to describe the shaded portions of the Venn diagrams, okay? Now, let me just say, for most problems like this, there is more than one correct answer, and you'll see that here in a second. All right, so here we have all elements that belong to A or B, but not both, all right? So that kind of suggests this first answer to me. The complement of A intersect B relative to A union B. So everything that belongs to A or B, but does not belong to both, okay? I wouldn't have thought of these other two answers, but if you did, they mean exactly the same thing. All right, here we have, let's see, well, this set here is A intersect B, and this is B intersect C. So I probably would have come up with this answer, but that is the same exact thing as this. This is actually an example of the rule that we looked at on the previous slide, all right? In order to get into this set, this green shaded set, you must be a member of B, and furthermore, you must be a member of either A or C, okay? But I will admit this is the answer I thought of first. And after that, they get a little more complicated. Well, at least letter D is a little more complicated. So the shaded region in C is everything that belongs to only set A and not set B or set C. So when I say it like that, all elements that belong to A but do not belong to B or C, that makes me think of this second answer here, okay? The other two answers also work. I don't think I ever would have come up with this one, okay? All right, now D is kind of ugly. I don't even know a simple way to describe this. It looks like you start off with A union C, then you throw out everything that's in B, except you need this part back, all right? So let me just say that if this, let me bring my pen up here for a second. If this little shaded region was not here, then this would have been a lot simpler. We could have just said the difference of A union C and B, all right? Everything that is in A union C but is not in B, okay? However, that would only give us, you know, these three shaded regions out here. It wouldn't give you this one. So let me show you the answer I thought of. A couple of these answers are just ridiculously complicated. I think I would have probably gone with this first answer. So this is saying start off with the difference of A union C and B, which is these three regions over here. And then the simplest way to pick up this middle region is to take the union of that set with A intersect B intersect C. All right, A intersect B intersect C is what all three sets have in common, so that's exactly where I put the X. Never in 100 years would I have come up with this answer, okay? All right. If you're doing online homework, I have a feeling that these online homework exam problems will probably be multiple choice, just a guess. All right, let's see what else we got. All right, so here's another example. Suppose M is the set of all students taking mathematics, and E is the set of all students taking English. Identify the students described by each region in the figure labeled A, B, and C. So A would be the students who are taking mathematics, but are not taking English, right? Which, remember, we use this set notation to write that set. B is the intersection of M and E. So those are the students who are taking both mathematics and English. And then finally, I bet you know what C is. Those are the students who are taking English, but not mathematics. The complement of M relative to E. Oh, and then I didn't even notice region D over here. So these would be students who are taking neither English nor mathematics. And you can write that either one of these ways. It's kind of interesting that these two sets are equivalent. That's actually called De Morgan's law. I don't think we're going to get into that in any detail, but that's what that's called. All right, I'm going to use my tablet for this one. In a survey that investigated the high school backgrounds of 110 college freshmen, the following information was gathered. 25 are taking physics, 45 are taking, took, this is supposed to be what they took in high school. 25 took physics, 45 took biology, 48 took mathematics, 10 took both mathematics and physics, 8 took biology and mathematics, 6 took physics and biology, and 5 took all 3 subjects. And based on that information, they want to know how many students took biology but neither physics nor mathematics, how many took physics, biology, or mathematics, and how many did not take any of those 3 subjects. So I am going to switch over to my tablet where I have already written down the information that they gave me on the previous slide. Should come up here in a second. There we go. All right. So I'm going to make a Venn diagram for this. Now, remember what I said earlier, don't read into those statements that they made. So when they say 25 students took physics, they did not say that 25 only took physics, and that's the only class they took. A lot of students read it that way at first. So I'm going to make my diagram, and I'm going to put physics right here. I'm going to put biology over here, and I'm going to put mathematics, down here. Okay, so with a problem like this, you really want to start in the middle, start with the intersection of all 3 sets, and then work your way out. So notice it says that all 5 students took all 3 courses. So I know that means that those 5 have to go right here, okay? Now I'm gonna work my way over to these 2-way intersections. There are 6 students who took physics and biology. That includes the 5 who also took mathematics. So the number that I'm going to put in this region right here is going to be 6 minus 5, which is 1. And then I'm going to do the same kind of thing for biology and mathematics. It says that 8 students took biology and mathematics, and that includes the 5 that also took physics. So in that region, we're going to have 8 minus 5, which is 3. And the same thing for physics and mathematics. 10 students took physics and mathematics, including the 5 that also took biology. So in this region right here, we're going to have 10 minus 5, which is 5. All right. Now we can work our way out to the big sets. 48 students took mathematics. That includes these 5, and these 3. So the number that I want to put in this region right here is going to be 48 minus 5 plus 5 plus 3. And that's 48 minus 13, which is 35. So that means 35 students took only mathematics. And then I'll do the same thing for biology. 45 students took biology, but that includes this 1, these 5, and these 3. So we're going to subtract 1 plus 5 plus 3, which is 9. Oops. So that should be 36. And then 25 students took physics. That includes these 5, and this 1. So 25 minus 5 plus 5 plus 1. Is 25 minus 11, which is 14. Okay, now there's one more number to fill in. Remember, there were 110 students total. I forgot to write this down at the beginning, because presumably there are some students who did not take any of these courses. So what we need to do now is add up all the numbers that we have in the diagram and then subtract that from 110. So let's see. 14 plus 1 is 15, plus 5 is 20, plus 5 is 25, plus 3 is 28, 28 plus 36 is 64, 64 plus 35 is 99. So I believe this number should be 110 minus 99, which is 11. All right, so now I believe that this diagram all filled out is in the PowerPoint. So I'm going to switch back to the PowerPoint, and we should be able to do everything else we need to do from there. All right, so here is the diagram, and I'm looking at their diagram, and I'm looking at my diagram, and everything looks the same. All right, so the first question was, what was the first question? How many students took biology, but neither physics nor mathematics? Well, that would be the 36 students that you see you know, right under the letter B. I think here, yeah, on that last slide, they were just explaining some of the work that we already went over. And I think they're still doing that. Okay, 36 students took biology, but neither physics nor mathematics. The second question was, how many students took physics, biology, or mathematics? That would be the 99 people that we added up. Okay, so they're still filling out their diagram. Okay, the number of students who took physics, biology, or mathematics is 99. And then because the total number of students is 110, the number that did not take any of the 3 subjects is 11. All right, Cartesian product. One way to produce a set from 2 sets. We should say another way because we've already talked about several. Another way to produce a set from 2 sets is by forming pairs of elements of one set with the elements of another set in a specific way. Suppose a person has 3 pairs of pants, blue, green, and white, and 2 shirts, which are blue and red. According to the fundamental counting principle, there are 3 times 2 equals 6 possible ways to pair an element from set P with an element from set S, forming a set of ordered pairs. I remember talking about this a section or two ago. And here are the 6 ordered pairs. So this one here means blue pants with red shirt. This means white pants with red shirt. That means green pants with red shirt. Blue pants with blue shirt, white pants with blue shirt, green pants with blue shirt. Because the first component in each pair represents pants and the second component in each pair represents shirts, the order in which the components are written is important. All right, and then 2 pairs are considered equal if and only if the first components are equal and the second components are equal. A set consisting of ordered pairs is an example of a Cartesian product. So here is the official definition. For any sets A and B, the Cartesian product of A and B, which is written like this, A cross B, is the set of all ordered pairs such that the first component of each pair is an element of A, and the second component of each pair is an element of B. So in set builder notation, it's the set of all pairs, x comma y, such that x is an element of A and y is an element of B. Notice that I read this as A cross B. It should not be read as A times B for the same reason that you don't read the complement of B relative to A as A minus B. Right? Times is something you do to numbers. It is not something you do to sets. All right, so an example of Cartesian products, if A is the set A, B, C, and B is the set 1, 2, 3, find each of these Cartesian products. So this is really easy. You just make ordered pairs where the first component comes from A and the second component comes from B. You can also figure out ahead of time how many ordered pairs should be in the answer by multiplying the cardinality of A times the cardinality of B. So since each of these sets has 3 elements, each of these Cartesian products should have 9 pairs. So here are the pairs that belong to A cross B. Notice there are 9 of them. Here are the pairs that belong to B cross A. And then finally, it does make perfect sense to take the Cartesian product of a set with itself. And that would look like this. So it also has 9 ordered pairs in it. It is possible to form a Cartesian product involving the empty set. Suppose A is the set containing 1 and 2. Because there are no elements in the empty set, there would be no ordered pairs x comma y with x belonging to A and y belonging to the empty set. So if you try to take the Cartesian product of a set with the empty set, you just get the empty set. And that makes a lot of sense because if you think about cardinality, A has 2 elements and this set has 0 elements, so the Cartesian product should have 2 times 0, which is 0 elements. Similarly, the empty set cross A will always come out to the empty set. That does it for section 2-3, and that does it for chapter 2. So we'll see you next time, starting chapter 3.